Good morning, good afternoon. Welcome to HITEC's webinar on multi-axis force sensors as used in robotic applications. I'm George Lowe, HITEC's Vice President and Managing Director. HITEC has two manufacturing facilities with our headquarters located just outside Boston, Massachusetts in the US, and also our Aerospace Center of Excellence located in Sri Lanka. I've been with HITEC over 35 years now, having started my career within the engineering department. HITEC serves all markets in all industries, with biomedical, industrial, and aerospace and defense being our largest. A quick look at the world of humanoid robotics. You've likely heard of some of these, if not even witnessed some of these in action. Robots such as Tesla's Optimus, Figure AI's Zero One, Unitree's G1, and Boston Dynamics Atlas. Naturally, there are other players in the industry too, such as Agility Robotics Digit and Apptronic's Apollo, all of which prove that the market is growing and innovating while the technology continues to improve. On the industrial side, nearly 4.3 million robots were used in factories in 2023, which is the last year that data is available. There's also significant automation adoption anticipated in various areas over the coming years, such as warehousing, material handling, essentially anywhere where tasks can be efficiently handled by a robot. On the humanoid side, market is expected to grow quite large, becoming a $38 billion market by 2035. As you can see by the data, massive growth is expected for units deployed over the next 10 years, resulting in roughly 400% growth within that market space. Strain gauges are used throughout a robot, sometimes on the robotic component itself, but also within bespoke sensors which are deployed throughout the robot, including joints and limbs, essentially anywhere where a force or a torque or pressure needs to be measured or monitored. And now I'd like to introduce Dominic Alashkar, HITEC's Director of Engineering. He's going to walk us through various application examples that HITEC has worked on, including areas such as haptic touch, pilot controls, warehousing, surgical, and also prosthetics. Welcome, Dominic.
Thank you, George. Good morning, good afternoon, and good evening. My name is Dominic Alashkar, and I've been with HITEC for 21 years, with 3 years working for an off-the-shelf load cell company designing precision, gold standard load cells. During my time at HITEC, I managed both engineering teams in the US and Sri Lanka, overseeing the aerospace, medical, automotive, robotics, industrial, and oil and gas industries. In this webinar, we will explore why strain gauge are essential parts of humanoids, how they impact that industry, and the benefit they impose on our future. Please note that at HITEC, we service thousands of applications in the industry, and some are in the robotics and humanoid sector. We selected only a handful of applications for this webinar, but we'll be open to discuss with you any special application that you may have. We offer turnkey solutions from development to high volume production and the hundreds of thousands of units per year using automation and other proprietary methods. Why use strain gauges as opposed to other technologies? Strain gauges have high sensitivity, they are flexible and precise, work well in static and dynamic environment, and have a very high resolution. Load cells provide an accuracy of 0.03% to 1.1% approximately of full-scale load. It is calculated by taking the square root of sum of the squares divided by number of elements, where you would be looking at hysteresis, null lane, creep, temperature, effect, and combined error, or extended error of bias. Difference between the measured reference and true values. That's what SEB means. Standard error of bias. This can resolve into a sensitivity of subgram forces depending on the full scale, with forces that are felt when pressure is applied by finger. The use of multi-axis helps in detecting various forces such as pressuring the finger, twisting, bending, and moment loads. Example, hooking a bag in the middle of the finger while trying to pull up will cause some moment forces instead of pure bending when the bag is at the tip of the finger. From data acquired, one can teach the humanoid to detect the type of skin, detect if the skin is hydrated, as dry skin shows a stiffer surface with more curves versus hydrated skin that is a smooth skin. Human touch is relatively temperature compensated through neural adaptation, and the load cell is similarly compensated for temperature. So, how do strain gauges replicate human touch? Human touch can detect forces in the millinewtons range, less than 10 to the minus 3 newtons, which is approximately 10 thousandths of a newton. While most foil strain gauge systems have the ability to detect forces between zero point zero 0.01 and zero point 0.1 newtons, semiconductor gauges increases the sensitivity to detect forces closer to human touch down to 0.001 newtons. That's 10 times more sensitive than foil. The latency can now mimic that of human in response time, especially in fast changing conditions. Low noise floor and high sampling rate help with improving the latency that mimic that of human touch and response time. It also mimic faster response to gripping and subtle texture changes. Strain gauges have different sensitivities. For example, semis being the most sensitive, having a gauge factor up to 150, which is about 75 times more sensitive than that of foil using gauge factor 2. So some of the benefits of human touch with strain gauges: load sensors react appropriately to loads, allowing it to differentiate between hard tools and soft objects. Human-like interactions measure down to zero point 0.1 gram of force of measurements. With 0.03% accuracy, this can be achieved. Some load cells are designed with mechanical overload protection, which can be tuned to certain displacement, and others are combined with safety overload specifications up to 150% to 200% of the required full scale. This is needed as this can happen due to exercise and excessive load, unexpected impact if the robot bumps into something, and also measuring torque and shear forces when using 6-axis or multi-axis load cells. Benefiting by adaptive functionality such as changing or grip and movement based on sensed forces. What are the business impacts? Reduced downtime, as an example, through less fatigue time, less breaks, fewer incidents. With improved yield standpoint, this results in improved quality, repeatability, and more consistency with less scrap. Moving on to passive and active flight control stick applications, what are the challenges that pilots face using a passive stick? In passive sticks, the challenges lacks providing any data and information, such as modern aircraft require precise input from pilots for navigation, especially in high-stress situations like combat or turbulence. Conventional passive control sticks rely on mechanical or simple electronic systems to detect input for haptic feedback, which may not provide the granularity or feedback required for optimal performance. This can lead to reduced control accuracy, pilot fatigue, and challenges in maintaining stability during critical maneuvers. So some of the challenges are we don't have any force feedback, none of that. Pilot synchronization is not linked in dual cockpit between two pilots or with the ground. System awareness, you have no cue of system behavior, autopilot flight envelope, and also no haptics. No visual or auditory only. You would be seeing some safety alerts due to visual or auditory only aid. Training aids have weak muscle memory, no resistance, relies on memory of the pilot, and there's no resistance to natural elements. And you don't have any envelope protection, meaning that the pilot cannot feel any limits. So what makes a grip active is providing sensors to the grip. At HITEC, we designed a 6-axis sensor to transform passive sticks into active ones. This provides high accuracy force measurements to 0.5% of full-scale loads, magnitude and direction of force applied to the stick, real-time feedback with control limits, resistance warnings, overload mechanical protection with safety overload design. Stick applies counter force stall for or G limits. Future autonomy assisted cockpits where a human and AI co-pilot share control stick. Both sticks mirror each other in real time. When one pilot moves their control stick, the other stick physically follows the same motion in real time. This made possible through sensors, including strain gauge load cells or force sensors. The system creates a tactile and synchronized connection between both pilots or between pilot and co-pilot controls. Support team-based control, especially in complex scenario, example aerial refueling, landing in crosswinds, where the feedback can be seen in real time through data transmitted back to the base. Essential in future autonomy assisted cockpits where a human and AI co-pilot share a control stick. With a programmable synchronization feedback to pilot, both pilots are instantly aware of control inputs, reduces the chance of conflicting inputs or miscommunication. Active stick can also help with the training and instruction. Perfect for fly instruction, students can feel exactly how instructors are correcting them and vice versa. So why use force feedback for flight control sticks? You get enhanced precision by about 80%, moment sensitivity with longer arms, longer moment, and force being applied. There's better maneuverability as a result. Improved pilot feedback, real-time haptic feedback, preventing asymmetric control issues. Some of the business impacts are improved payload efficiency by haptic feedback and ability to measure the load and set up triggers and alarms if load has exceeded its limit. So it improves time and increases revenue. High loads causes high stress, which could result in wear of components and premature fatigue over time. Monitoring stress and preventing overload to reduce stress and increases longevity of the aircraft. Our next application discusses robotics used in modern warehouses and the challenges they face. With manual systems, warehouses often face inefficiencies such as inaccurate weight measurements, misidentification of items, and overloading of transport equipment. These issues lead to slower operations, increased error rates, equipment damage, and even safety hazards for workers. Delivering warehouse automation through strain gauging and robotic arms or conveyor systems, sensors are placed to measure forces and moments during pick and lift operations. This helps with safety overload up to 150% to 200%, higher accuracies of 0.1% of full scale, faster response time, greater than 100 million cycles of fatigue of the load cell, reduced temperature effects, data-driven integration. Integrating strain gauges and six-axis load cell into automated warehouse systems can address these challenges by enabling precise weight measurement, real-time feedback, and load monitoring. High-tech transducerized solutions designed through enhanced FEA analysis and analyzing moments and models for optimum strain gauge locations. In robotic arms or conveyor system, gauges are placed to measure stress and strain during picking and lifting operations. This helps with detecting subtle deformation to prevent overloading or mishandling of items, measuring the weight of the item and embedding it in shelving units to create more space. Provides accurate load data with 0.1% accuracy to ensure items are within their weight specifications and reducing errors in packaging and shipping. Increase storage by enabling you to stack pallets on top of each other, weigh each item accurately to create proper shipping documentation in real time, and optimize storage. Strain gauges provide instantaneous force and load feedback This enables automation systems to react in real time, skip extra sensing or safety delays, accelerate pick and place operation by minimizing retries and errors, and eliminating of redundant processes. With high confidence and accuracy load detection, systems don't need to double check positions and or rates. No need for external scales or delay, including checkpoints. Seamless integration means less mechanical complexity, resulting in smoother operations. Some of the business impacts: higher throughput, more orders are processed per warehouse, um, equal and better revenue per square foot, lower labor cost, automation handles more in less time, reducing human touch point and better ROI with reduced cycle time. Moving on to medical robotics surgical applications. Currently, with surgical procedures relying heavily on manual and visual processes, inexperience results in no tactile feedback. Surgeons cannot feel the tissue resistance, the tension, or force. Higher risk of damage in robotics assisted surgeries, replicating the fine, precise motion of a surgeon's fingers and the movements of a surgical tool is significantly challenged. Lack of awareness: instruments may apply too much or too little force without real-time measurements. Conventional systems often lack the sensitivity to capture subtle forces or the ability to translate complex motions into accurate tool movements. Difficult tissue differentiations: cannot distinguish between soft versus tough tissues without force sensing. This can lead to reduced dexterity, limited feedback for the surgeon, and potential harm to the delicate tissues. Increased error rate, such as risk of puncturing vessels or tearing tissues due to blind force applications. And then training limitations: less natural hand-eye force coordination makes learning curve steeper. Using strain gauge-based sensors allows the measurements of slight deformation down to 6 decimal places. With forces applied, these small displacements from load cells, when integrated into surgical tools, are then converted into real-time force and moments, measuring down to 0.1% accuracies and then millinewton force measurements. These forces and moments are then fed into the surgeon's haptic interface or a feedback control loop for autonomous motion limits. An instrumentation amplifier and an analog to digital converter, ADC, are also used to amplify and digitize these tiny signals. These sensors are designed with autoclave protection. Benefits of tactile feedback for robotic surgery: one, you'd have high overload capability, designing with high safety labor, a safety factor of about 600% compared to off-the-shelf sensors, which are typically designed between 150 to 200%. Enhanced haptic feedback, which restores surgeon's sense of touch, better control, and finesse. Reduced surgeon fatigue, which reduces muscular and joint fatigue. With high overloads, the use of semi-strain gauges to detect subtle forces increases sensitivity typically by 75% or 75 times than that of regular force strain gauge. With haptic feedback, data from load cell is used to provide tactile feedback to surgeons throughout the control system. Strain gauge load cells reduce the need for exaggerated or repeated movements. This results in reduced time in surgeons' fatigue. Some of the business impact with risk mitigation: surgeons rely less exclusively on visual cues, making surgery more intuitive and less mentally draining. With less risks comes a reward, and that reward is covered by data collected and feedback to the surgeon, which will protect him from malpractice lawsuits. With improved efficiency, this means less surgeons in the surgical room, more data-driven analysis, AI failure prediction, and less opinionated decisions. Our final applications discusses prosthetic leg, turning a mechanical leg into a smart leg. Legs are used to help in our daily movements and transportation, but they are also but they also react to the terrain and can feel the roughness and smoothness of each surface that they step on. They carry our weight and react to heavy loads. Conventional prosthetic feet often struggle to replicate natural dynamics of human walking, such as balancing forces, adapting to uneven terrain, and providing real-time feedback. Users face issues with stability, comfort, and energy efficiency, which can lead to reduced mobility and increased physical strain. With our custom solution for integrated load cells and prosthetics, whether we use composites, titanium, or aluminum, as we keep cautious of not increase weight to the prosthetic, these sensors are positioned at the ankle, joint, or base of the prosthetic to measure forces and torques across 6 degrees of freedom, 3 linear and 3 rotational axes. A 6-axis load cell captures complex multi-directional forces experienced during walking, running, or navigating uneven terrain. The data collected from the sensor feeds the data back into a microcontroller that adjusts the foot stiffness, angle, or resistance dynamically to stimulate natural motion. Also, the data collected can teach the sensor to differentiate between different terrains, gravel or sand, provide feedback for weight carried, and send alarms if overweight has been detected. This elongates the life and wear of the prosthetic and prevents injuries that are hard to be felt by the patient. The strain gauges and load cell work together to analyze and replicate the natural load distribution and motion of a human foot, with overload protection and safety factor of a minimum of 150% of full scale. The load cell continuously measures the torque and multi-directional forces, allowing the prosthetic to adapt to uneven surfaces and changes in terrain. The sensor collects detailed data on walking patterns and load distribution with accuracies down to about 0.1%. As a business impact, with enhanced value-added services, developing platforms that collect and analyze sensor data in real time could position companies and make them essential partners in the prosthetic ecosystem to improve performance and the ability of these prosthetics to perform on any terrain, making them more attractive and easier to sell. With increased demand for high quality, comfort is key, and an active prosthetic being functional drives growth in the medical device sector. In conclusion, humanoid robotics are having an ever greater real-world impact with high-tech custom strain gauge technology enables advancement through improved accuracy, reliability, and repeatability. Humans are structures to feel and analyze. With integrated strain gauge sensors, we are allowing future humanoids to share our feelings and analyze smarter, become more consistent, and becoming more effective in solving difficult and mundane tasks. So why HITEC? We specialize in custom to OEM solutions that are automated driven, offer warranty on workmanship, and we focus on creating long-term relationship with customers, which is key to our success. These programs are often years long and creating a total customer satisfaction with high quality, low cost, turnkey solutions, and fast delivery is our way to thank the customer for partnering with HITEC. With that being said, I would be happy to take any questions. I'll be looking at the question and answers in this webinar that I would like to respond to. If you guys have any questions or you haven't typed it in yet, please do so, and I'll be glad to answer these for you. Okay, so we have 4 questions here in this session that came through. First one is, how does overload protection impact sensor durability and calibration drift over time? So looking at overload protection, essentially it's a mechanical overload that's being designed to allow minimal displacement of the sensor. So the sensor is designed to certain full scale, and that's required by the customer. That's the load that they would want to the unit to be seen, and then they have an safety overload, which where the part does not yield, but that would be basically before yield, before the ultimate plastic deformation occurs. You want to make sure that that part does not go into plastic deformation. So what we do with the overload protection, we would calibrate the unit all the way up to the full scale of the required loads, and then we would dial in the mechanically, whether we use a screw as an example or other mechanical features, we would dial it into that certain displacement so we don't allow any further displacement, but that would beyond the actual full scale load. Second question, what is the typical latency of HITEC strain gauge based multi-axis force sensor, and how does it compare to human tactile response time? Humans in general have a very fast response time, but with advanced data acquisition systems that we currently have, and with the sensitivity acquired from the sensors, those data acquisition systems have very high speed sample rates that can mimic very close to what humans can feel, and sometimes exceed that from humans. So it's essential to know what to choose for data acquisition system, and choose the correct sampling rate when you're doing the analysis. Another question came in is, how does strain gauge sensitivity compare between full and semiconductor technologies, and what trade-offs exist in real-world robotic applications? So as I explained in the presentation, semis are about have a gauge factor of about 150, which is typically 75 times more sensitive than a strain gauge regular foil. But they have their downfalls too with temperature compensation, and they're more sensitive to vibration as well. But with our methods and proprietary methods that we designed, we are able to compensate them properly. It has to do with the installation, preparation for those sensors to act properly within the system and give you the high accuracy requirements that the customer would need. We've been successfully doing these with multi-axis load cells and also with single axis by using our own proprietary, again, methods to reduce the temperature effect and vibrations. There is a question about bonding technology. So what bonding technology do you use for putting down semiconductor-based gauges? That's a good question. Again, some of it is our proprietary methods, but we use a specific type of adhesive. When we install the strain gauges, we use ovens, which is vacuum-based ovens as well, where we cure these a certain period amount of time to bond the semis together properly. There's techniques also for wiring to be able to reduce some of the effect of that causes from the wire that causes thermal effects. But bonding in general, it has long time curing, and some of that takes 24 hours to 48 hours using some vacuum ovens. And last questions: how do environmental factors like temperature variation or mechanical variation affect the performance and accuracy of the sensors? Oh, there's a follow-up question here. So so to answer the environmental effect of temperature at first, we're looking at, when we're looking at transducers, there's always effect of vibration or temperature or other elements. We typically test these separately without including any force induced forces. Now, eventually, you're looking at strain, and you're relating that strain into forces. But with the other elements and factors, you want to test these separately and then reduce that effect on the strain gauge bridge. We do that by using certain resistors that we implement inside the Wheatstone bridge to reduce that effect of the other elements. So follow-up question back on the semiconductor: if we expect stability of semiconductor-based sensors. With our proprietary methods for temperature compensation, we've seen these our semiconductor gauges to be fairly stable. There's some effects of, for example, light that could affect those semiconductor gauges. So using proper protective coating, which is dark, pretty much does not have a light effect. So there's a lot of factors that I mentioned between long time curing, the type of how you wire these together, and there's a proprietary formula for temperature compensation that we use for balancing the bridge properly to allow perfect temperature compensation. We've worked a tremendous amount of time on this subject for about 3 years at HITEC, back and forth to do some research and development to develop that process. So we'll be glad to take some questions offline if you would like more details or work with you on that certain application to be able to allow basically high accuracy results from your sensor with proper endurance and proper rigidity of your sensor. Are your prosthetic six-axis sensors foil-based or semi-based gauges? So that's a good question. It's mainly foil-based strain gauges because the load applied is not very small. Pretty much you get the weight of the human body as your preload, or sometimes if you lift your leg, that's your zero, which starts around, 100 pounds or less, depends on the size of the person, or more, of course. The weight measurements, we're not going into grams or subgrams. If the requirements for safety factor or the ratio is very high, where the requirement is 10 to 1, or 6 to 1, or 5 to 1, then you would look into semiconductor gauges. But if you're looking 2 to 1 ratio or 3 to 1 between the weight of the person, what your minimal weight is you're looking for, you tend to want to use foil-based gauges to make sure there's less effect of temperature and sensitivity from other factors. So with that being said, I would like to thank you for joining and thank you for your time and attention, and we hope to hear from you in the near future. Please contact me if you have any questions. We'll be glad to assist you. Thank you for joining and thank you for your time. Good evening.